A beam of light cuts through absolute blackness, and for a moment, the ocean stops feeling like water and starts feeling like outer space. 1,700 meters down, in water colder than your refrigerator, something drifts into frame that looks like it was designed to break your sense of what a fish is allowed to be. It has almost no color and almost no shadow, just a delicate outline and a head that appears to be made of glass. Beneath that clear dome, luminous green eyes rotate slowly, scanning upward through the dark for prey that will never understand it is being watched. This is not science fiction. This is an ordinary day in the deep ocean. So why does life become stranger the deeper we descend? As if evolution itself starts to dream in a different language once the sun is gone? What pressures twist bodies into transparency, into living shadows, into creatures that carry their own light like a weapon? And what does the ocean keep hidden in places where sunlight has never reached? Not once, not ever. Here is the uncomfortable truth behind every deep-sea documentary you have ever watched. We can map, and we can measure, and we can estimate. But seeing is another matter entirely. A sonar map can tell you where the seafloor rises and falls, where a trench opens like a wound, where a ridge climbs like a spine, but it cannot tell you what is alive in the folds of that terrain, what hunts in the water above it, what blooms and vanishes in the cone of a camera light. Much of what we know about the deep is still stitched together from brief dives, narrow beams, partial samples, and fragile bodies that do not survive the journey upward. In a sense, we have been trying to understand an entire planet by peering through a keyhole, and sometimes the keyhole is fogged, and sometimes it is cracked, and sometimes what we see passes by too quickly to name. Which means that, right now, there may be animals moving through the darkness that no human has ever seen alive, living full lives in a world we can barely reach. The deep ocean is not just unexplored. In many ways, it is still unknown. We begin our descent in the sunlight zone, the first couple hundred meters, where the ocean is familiar enough to feel like home. Here, light pours through the surface and turns the sea into a living engine. Photosynthesis fuels microscopic phytoplankton, which feed zooplankton, which feed small fish, which feed larger predators, and energy moves upward through the food web like a rising tide. Coral reefs blaze with color. Schools of anchovies flash silver in tight, synchronized turns. At the surface, life looks abundant and loud and effortless, as if the ocean is an endless banquet. But this bright layer is thin. It is a sunlit skin stretched over something incomprehensibly vast. And if you want one sentence that explains the entire descent we are about to take, it is this: in the surface ocean, survival is paid for with sunlight, and below it, everything must live on whatever change the light leaves behind. We sink past 200 meters, and the blue begins to drain away. The world dims, not like a sunset, but like a room where someone is slowly turning the lights down without telling you when they will stop. This is the twilight zone, the mesopelagic, a realm that can stretch down toward 1,000 meters. Photosynthesis becomes impossible. No plants can grow here. The energy source that powers the surface ocean is gone, and for a moment, it seems like the story should end. But it does not end. It mutates, because life in the twilight zone does not run on sunlight. It runs on leftovers. If you look closely, you start to see it falling past you in an endless, quiet blizzard. Tiny flakes and threads, pale specks descending through the water column. Scientists call it marine snow. It is dead plankton and fecal pellets, shed mucus and fragments of tissue, the remains of things that lived in sunlight and are now sinking toward darkness. It sounds unpleasant, and it is. But it is also everything. Marine snow is one of the primary food sources that connects the sunlit world to the deep, the only steady stream of calories drifting down into places that will never see the sky. Imagine living in a desert where the only food arrives as crumbs falling from an airplane you will never see, and you have a sense of what most deep-sea animals are dealing with. Every flake matters. Every drifting particle is a meal or the promise of one. Now layer in another pressure the surface ocean rarely thinks about. In parts of the twilight zone, the water can hold remarkably little oxygen. These oxygen-poor layers, often called oxygen minimum zones, are like invisible altitude for marine life. Breathing becomes harder, movement becomes expensive, and wasteful biology becomes a death sentence. In that thin-breath world, many animals slow down, conserve energy, and evolve bodies that are less about speed and more about efficiency. And that leads to the Twilight Zone's first great obsession. Not strength, not size, but invisibility. In the twilight, survival is paid for in shadows, and the best shadow is the one no one can find. Some creatures solve that problem by erasing themselves. Transparency becomes a form of armor. A glass squid drifts with a body like living crystal, its outline dissolving into dimness, its organs reduced to faint smudges. A glass octopus can be so clear that its eyes look like the only solid parts, two dark coins suspended in water. If you are transparent enough, a predator searching for a silhouette finds nothing but the gloom it already expects. And then there is the barreleye again, the fish with the glass head. A creature so strange that for decades, even when humans caught it in nets, we could not truly understand what we were seeing. Its head is enclosed in a transparent, fluid-filled shield, and inside that dome its tubular eyes can rotate, tracking prey above, while delicate tissues are protected from stinging tentacles. When researchers finally filmed it alive in its own world, with deep-sea cameras designed not to destroy what they were trying to observe, the mystery snapped into focus. The dome was not an accident. The dome was the point. Evolution had built a skull you can see through, in a realm where seeing first means surviving longer. But transparency is only one answer. Some animals do the opposite. They do not disappear. They make themselves visible on purpose. Because here is the paradox of the Twilight Zone. Darkness is not absolute yet, and that faint light creates danger. If you look up, you may still see a dim glow, like a distant ceiling. Any animal swimming overhead becomes a silhouette against that glow, and predators hunting from below can see you as a dark shape cut out of the light. Unless you cheat. Many Twilight Zone creatures grow light-producing organs along their bellies, tiny biological lamps called photophores. By adjusting the brightness to match the downwelling light, they erase their outline. From below, they stop looking like a silhouette and start looking like empty water. This is counter-illumination, the closest thing nature has to a cloaking device, making light in order to disappear into light. And it is not a static trick. The brightness above changes with waves, with clouds, with time. In the deep, there are animals that can calibrate their belly glow in real time, dimming and brightening to maintain invisibility as the world above them flickers. It is an astonishing thought. A living creature actively tuning itself to the sky it will never touch. Because the sky controls whether it lives. Once you understand counter-illumination, bioluminescence stops being a novelty and becomes what it really is in the deep sea. A language, a tool, a trap, a warning, a disguise. In the open water, far from any rock or reef, light is one of the only ways to influence what happens around you, which leads to one of the strangest moments in the history of human technology in the ocean. A mystery that arrived not in a lab, but in war. During the Second World War, sonar operators began reporting something impossible. Their instruments detected what looked like a solid layer in the water, like a false seafloor hanging hundreds of meters below the surface. Even stranger, that layer rose at night and sank at dawn. It behaved like a phantom seabed, appearing and disappearing, moving like a living thing. For a while, no one could explain it. Then the explanation arrived, and it was stranger than any malfunction. The seafloor was not geology. It was biology. Billions upon billions of creatures were moving together every night, rising through the water column under cover of darkness to feed, then retreating downward before daylight returned. This daily movement is called vertical migration, and it may be the largest synchronized migration of life on Earth by sheer numbers and biomass. Lanternfish, krill, copepods, squid, jellies, an entire invisible world climbing and falling in a rhythm older than humanity. Here is the first twist, and it is the kind of twist that changes how you see the whole planet. This migration is not only a feeding behavior, it is a global machine. When those animals rise to eat near the surface and then sink again, they carry carbon downward in their bodies and in their waste, moving the products of sunlight into the deep. In other words, the twilight zone is not just a habitat full of strange creatures. It is part of the ocean's biological pump, a vast living conveyor belt that helps regulate the chemistry of the sea and, indirectly, the atmosphere above it. The deep scattering layer was not merely a curiosity on sonar, it was the heartbeat of an unseen system that connects the surface world to the abyss. We continue our descent. At around 1,000 meters, the last traces of sunlight vanish. We cross into the midnight zone, the bathypelagic, a realm that can extend down toward 4,000 meters. Here, there is no dawn and no dusk, only permanent night. The water temperature hovers near freezing. The pressure becomes monstrous, pressing in from every direction with a force that can make metal creak. The deep is no longer simply dark. It is heavy, and that weight shapes everything that lives here. To a human body without protection, this is lethal. And yet life persists, not by resisting the environment, but by surrendering to it in brilliant ways. In the midnight zone, light stops being something you use to see the world. It becomes something you use to control it. If the twilight zone is about hiding in faint light, the midnight zone is about manufacturing light because there is none left to steal. Some predators create small, deliberate glows to lure prey closer, a floating beacon in an infinite dark. Anglerfish are the emblem of this strategy. A female drifting with a bioluminescent lure dangling from a modified spine, waving gently like bait on a line. In that blackness, curiosity is dangerous. A smaller fish approaches the glow, expecting food or a mate, and finds instead a mouth armed with teeth like needles, a jaw that can open wider than seems possible, and a stomach willing to stretch around whatever the ocean provides. Because in the deep, you do not get picky. But the anglerfish is not just a hunter. It is an answer to a terrifying problem. How to reproduce in a world where you may never meet another of your species. In certain anglerfish lineages, Males are tiny compared to females. Built for one purpose: find a female by scent and touch and chance, and then latch on. Over time, he begins to fuse to her body. Their tissues merge, his organs reduce. He becomes, in effect, a permanent reproductive partner, nourished by her blood, ready when she is ready. It is extreme, unsettling, and perfectly logical when you remember the scale of the ocean and the darkness that hides everyone from everyone else. Now shift your attention, because the midnight zone has another form of invisibility, one that feels even more unnerving than transparency. Some fish do not try to vanish by being clear. They vanish by becoming blacker than the darkness around them. Researchers have documented deep-sea species with ultra-black skin that reflects almost nothing. Under a submersible's spotlight, they can look like holes punched into reality, living silhouettes that refuse to reveal texture. Their skin is structured to trap photons, bouncing light into layers of pigment until nearly none escapes. In an ocean filled with bioluminescent flashes, that kind of darkness is camouflage. If the twilight zone taught animals to hide their outline, the midnight zone teaches them to erase their existence. And then there are predators that do something even more unsettling. They turn light into a private weapon. Consider the dragonfish, a creature that seems designed for secrecy. Most deep-sea animals produce blue-green light because those wavelengths travel best through seawater, and most deep-sea eyes are tuned to detect them. But some dragonfish can produce red bioluminescence, a color that is effectively absent in the deep because red light does not travel far and is quickly absorbed. Many deep-sea animals cannot see red at all, so the dragonfish's red glow becomes a secret flashlight. It illuminates prey without the prey ever knowing it has been revealed, and the dragonfish's visual system is adapted to detect what others cannot. In a realm defined by darkness, it has invented a private wavelength. Now picture a deep-sea expedition in real time. You are in the control room, watching a screen that is mostly black, speckled with drifting particles that look like snow in a flashlight beam. The remotely operated vehicle moves forward, and its lights carve out a tunnel through the abyss that ends abruptly in darkness, because the darkness is not a background. It is a wall. The pilot adjusts the thrusters. The camera pans. A faint shape appears at the edge of the beam, and then vanishes, as if the ocean swallowed it. Someone leans closer, certain they saw movement. Then a pinprick of light appears, hovering ahead, too steady to be a reflection, too deliberate to be random. It pulses once, twice, and the camera swings toward it. The lure is the only visible thing, a lonely star in a universe of water. And behind it, the predator is waiting, almost entirely lost in its own engineered darkness. Here is the second twist, and it is easy to miss if you only think of the deep as a horror show. The midnight zone is not a place where life is constantly sprinting and fighting. It is a place where life often wins by waiting. Energy is expensive here, so many predators do not chase, they ambush. Many prey do not flee, they drift. Metabolism slows. Movement becomes deliberate. In the midnight zone, survival is paid for with light you can manufacture, oxygen you can stretch, and time you can afford to waste, because the winners are often the ones who can remain patient longer than the ocean remains generous. We descend past 3,000 meters, and the water does not change in color because it has no color left to give. Then we pass 4,000 meters, and the open water gives way to the abyssal plains. The seafloor spreads beneath us like a different planet, a vast desert of fine sediment, soft mud, accumulating grain by grain from the slow rain of marine snow above. There are no reefs, no forests, no familiar landmarks, just an immense plain stretching beyond the reach of our lights. The pressure here is hundreds of times greater than at the surface. The temperature stays near freezing. Food is scarce, often arriving as the faintest trace of falling debris. Scarcity does something strange. Sometimes it makes life smaller and slower. Sometimes it makes life larger. Deep-sea gigantism is one of the ocean's enduring puzzles. Creatures related to small, familiar animals can become enormous at depth. Giant isopods, relatives of the little pill bugs that hide under rocks on land, can grow to lengths that feel absurd for their lineage. Amphipods, normally tiny shrimp-like scavengers, can become hand-sized. In the deep, it is as if the volume knob on evolution has been turned in unexpected directions. Why would a harsh environment produce giants? Scientists have proposed multiple explanations, and none alone solves the mystery. Cold temperatures can slow metabolism and extend lifespans, giving animals more time to grow. Scarce meals may favor bodies that can store energy and survive longer between feedings. In some settings, lower predation pressure may reduce the need for constant speed and allow investment in size. The deep sea is not one environment but many, and gigantism likely emerges from a combination of pressures rather than a single cause. What makes it haunting is that we still do not have a clean answer, because the abyss does not volunteer its laws. What we do know is that life down here often runs on a different clock. Many abyssal animals grow slowly, reproduce rarely, and live long lives. When food arrives as a slow snowfall, urgency becomes a waste. Patience becomes a strategy. In the abyssal plains, survival is paid for with endurance and luck. The endurance to outlast long stretches of hunger, and the luck to be near the rare moments when the ocean becomes generous. And sometimes, generosity arrives in the most dramatic form imaginable. A whale dies at the surface. A body weighing tens of tons begins to sink, carrying with it a vault of energy in the form of blubber and bone. Days later, it reaches the abyssal sea floor, and in a world where food often arrives as flakes, this is not a meal. This is an oasis. The first to arrive are the fast scavengers, drawn by chemical traces spreading through the water like a scent trail. Hagfish twist into the carcass. Sleeper sharks circle and bite. Rat tails hover. Amphipods swarm in such numbers they can look like living sand. Flesh disappears, and over weeks and months the whale is stripped to bone. But the story does not end with bones. In the deep sea, bones are not the end of life. Bones are the beginning of a second ecosystem. Bones are storage. They hold oils locked inside like sealed reserves. And down here, there are animals that have evolved to break into those reserves in ways that would seem impossible on the surface. Deep-sea researchers exploring whale falls discovered worms carpeting the bones, crowned with red feathery plumes waving in the current. These worms had no mouth, no stomach, no digestive tract. Instead, they had root-like structures burrowing directly into the bone, and within those roots lived symbiotic bacteria capable of breaking down the lipids hidden inside. The worms were named Osedax, bone devourer, and they were a reminder that deep-sea evolution does not merely tweak familiar designs. It invents entirely new solutions when the environment rewards them. A whale fall can support a unique ecosystem for years, sometimes decades, as different communities arrive in succession, feeding and reproducing and fading away. When it is finally consumed, The larvae disperse into the black water like seeds, drifting until they find another corpse, or they do not. The deep sea is connected by rare windfalls, and life survives by being ready for them. We descend further. Around 6,000 meters, the abyssal plains begin to fracture into slopes. The terrain falls away. The seafloor drops into something steeper, deeper, more severe. We approach the trenches, the scars carved by tectonic forces where one plate slides beneath another and drags the ocean floor down into the underworld of pressure. We enter the hadal zone, named after Hades. The hadal zone is not simply deeper, it is different. Trenches are isolated, like valleys cut so sharply into the planet that they become separated worlds. Currents behave differently. Sediment funnels downward and accumulates. Food can collect in ways it does not on flat plains. And because trenches are scattered across the globe like rare wounds, each can become its own evolutionary island, shaping life in parallel, sometimes producing familiar patterns with unfamiliar species. The pressure in the deepest trenches becomes almost impossible to picture, pressing down with a force that can compress foam into a thimble and challenge the very stability of proteins. To surface life, it should be a biological wall. And yet life exists. Cameras and landers have filmed fish living in trenches at depths once considered beyond the reach of vertebrates. Snailfish, in particular, have become icons of this world. Small, pale, gelatinous animals that look almost unfinished, their bodies soft and delicate, moving through darkness as if the weight of the ocean does not matter. Their cells are stabilized by chemical compounds that help proteins keep their shape under crushing force. Their bones are reduced, their tissues adapted for pressure rather than speed. They feed on the swarms of amphipods that gather around any food that falls into the trench. Because in the hadal zone, opportunity is rare and must be taken when it arrives. At some point, deeper still, fish disappear and invertebrates dominate entirely. Scientists suspect there may be biochemical limits for vertebrates at extreme depths. Constraints tied to the chemistry of pressure stabilization and the costs of maintaining complex physiology under immense force. The exact boundary varies by trench and remains an active area of research, but the pattern is eerie. Go deep enough, and the ocean becomes a kingdom of creatures without backbones, scavengers, and soft-bodied animals thriving where fish cannot. Now here is the third twist, and it may be the most unsettling of all, because it is not about evolution. It is about us. Even in trenches, in the deepest, most remote habitats on Earth, scientists have found signs of human pollution, including microplastics in animals that live far below any sunlight and far beyond any coastline. The details differ across studies and regions, but the message is consistent. The hadal zone is not isolated from the surface world the way we once imagined. The trenches do not protect themselves from our footprint. They collect it. In a place named after the underworld, our debris has still managed to arrive. In the hadal zone, survival is paid for with pressure-proof chemistry and the ability to endure what should be unbearable. And now, increasingly, it is paid for with the consequences of a surface world that cannot see what it touches. Yet the deep ocean is not only a place of scarcity and scavenging. In some places, it erupts with life in a way that still shocks scientists, because it proves that sunlight is not the only engine that can power an ecosystem. Hydrothermal vents form where seawater seeps into cracks near tectonic boundaries, heats up deep in the crust, and blasts back out loaded with minerals and chemicals. The vent fluid can be scorching, and it can carry compounds toxic to most surface life, including hydrogen sulfide. In the cold, dark deep, it looks like smoke pouring from chimneys on the seafloor. When scientists first encountered these vents, they expected a barren wasteland. Instead, they found dense communities of life: giant tube worms, clams, shrimp, crabs, bacteria forming mats like living carpets. It was an ecological contradiction. How could so much life exist in a place with no sunlight and no plants? The answer rewrote biology textbooks. These ecosystems run on chemosynthesis, not photosynthesis. Microbes use chemical energy, not solar energy, to build organic molecules. Some live freely in the vent water. Others live inside animals in tight symbiosis. Tube worms, for example, have no mouth and no digestive tract. They host bacteria within a specialized internal organ, and their blood carries the chemicals the bacteria need. The microbes make food, and the worm becomes a living habitat for an invisible factory. In the deep sea, life can be powered by poison, by rock chemistry, by energy leaking from Earth's interior. It is as alien as anything we imagine on other worlds, and it raises a question that reaches far beyond Earth. If life can thrive on chemical energy and darkness here, what about the oceans beyond our planet? Icy moons like Europa and Enceladus likely hide global oceans beneath their frozen shells. If those oceans have rocky seafloors and internal heat, they may have vents too. And if they have vents, they may have the same chemical gradients that feed life in our own depths. The search for extraterrestrial life may not be about forests and sunlight. It may be about darkness, pressure, and chemistry, about worlds that look dead until a light cuts through blackness and reveals movement. And that brings us back to the question we began with, the question that grows heavier the deeper we go, the question that turns every discovery into another doorway instead of a final answer. Why does life become stranger with depth? Part of the answer is constraint. Darkness removes the most familiar sense. Pressure challenges every molecule. Cold slows every reaction. Scarcity punishes waste. Constraints force innovation, and innovation in the deep often looks like strangeness to surface eyes. Transparency, ultra-black skin, living lanterns, parasitic mating, bone-eating worms, secret red flashlights. Chemical ecosystems built on vent smoke. These are not random horrors. They are solutions, honed by selection, paid for by lives that did not survive. But part of the answer is also time. The deep ocean is old, and it can be stable for long spans compared to the surface. While shorelines shift and climates swing and extinctions erase forests and reefs, the deep can remain dark and cold and pressurized, offering evolution a patient workshop where strange solutions can accumulate. The deeper you go, the more you enter realms shaped by slow pressures over enormous timescales. And we are still sorting out the deeper mysteries. Why do some layers fill with transparent animals, while others favor darkness that absorbs light? Why is bioluminescence so widespread? And why do different species use it for such different purposes? Why do some lineages become giants at depth, while others become delicate and fragile? In many cases, scientists can propose strong hypotheses, but the ocean is hard to test. It is expensive to reach, difficult to observe, and unforgiving to equipment. Sometimes the hardest part is not collecting data. It is simply getting a second look. Because many deep-sea creatures are so fragile that when they are brought toward the surface, the pressure changes can destroy their structure. Their tissues are built for a world that never decompresses. Their bodies can collapse, distort, or disintegrate, leaving scientists with damaged specimens that do not tell the full story. For decades, we misread the deep because we could not keep it deep while we studied it. Only with modern cameras, gentler collection methods, and more frequent expeditions have we started to see animals behaving normally, alive, complete, doing the things evolution designed them to do. And every time we look, we find something that feels like it should not exist, which is exactly why it does. Now imagine the ascent. The pressure eases. The darkness softens into a dimness, then into a faint blue. The water warms by degrees. Somewhere above, sunlight waits, bright and familiar. And the surface world continues with its storms and ships and human noise. But the mind stays down there. Somewhere, right now, in a darkness no human eye has ever seen, a creature drifts. It may be transparent, carrying its organs like secrets. It may be ultra-black, absorbing the glow of living lanterns around it. It may carry bacteria that make light, or host microbes that eat chemicals that would kill surface life. It may feed on marine snow from a world it will never see, or on the bones of whales that died long before any human ever spoke a word. It does not know we exist. It does not need to. And perhaps that is the final lesson of the deep ocean. We talk about exploring it, discovering it, understanding it, as if the darkness is a locked room waiting for us to open the door. But the deep sea does not owe us its secrets. It has been here for billions of years, building life in silence under pressure, shaping bodies for a world that barely intersects with ours. The creatures we call strange are not strange at all. They are exactly what survival demands.